question was asked about problem 157 in section 2.3 in the calculus volume 3 from OpenStax. And the question says, use vectors to show that a parallelogram with equal diagonals is a square. Actually, this is false. A parallelogram with equal diagonals is not necessarily a square. It is certainly a rectangle. And let us explain. So we have a parallelogram down here in the lower left corner. A parallelogram means that the two pairs of sides are equal in length and parallel. You could take either one to be your definition. If the two pairs of sides are parallel, then they must also be two pairs of sides of equal length. So a parallelogram says the vectors, consider the points A, B, C, D. The vector AB is equal to the vector CD, equivalent or equal, and AC is equal to BD. This makes the two diagonals the vector from A to D, which is AB plus BD, and the vector from C to B, which is AB minus BC, AB minus AC. And to make this easier to write, let's just identify these vectors as U and V. So this diagonal is U plus V, and this diagonal is U minus V. That's a parallelogram. A square, besides AB equals CD and AC equals BD, has two other conditions. That the AB and AC adjacent sides must be equal, and that'll force all four sides to be equal. And the adjacent sides must be perpendicular, and that'll give you the four 90-degree angles. So to simplify our writing, let's let U represent AB, which is the same as CD, and V represent AC, which is the same as BD. Now when someone says the equal diagonals, they're referring to length, not the vector qualities of diagonals. So equal diagonals is measuring length, and this means that the length of U plus V is the length of U minus V. But that forces, square both sides, the length of U plus V squared and the length of U minus V squared to be equal. But remember, whenever you think length, you also think dot product. The length of a vector squared is the vector dotted with itself. So we dot U plus V with itself and dot U minus V with itself. Then we use the properties of dot product, namely that I can distribute the dot product, U dot U, U dot V plus V dot U, and since those are the same, that's 2U dot V, and then V dot V. On the other side, the same result, U dot U in the front, U dot V in the back, but minus 2U dot V in the middle. The parts that match you can simply cross out. U dot U, V dot V. And so you're left with 2U dot V's is the same as minus 2U dot V's. Or adding 2U dot V to both sides, 4U dot V's is 0. But that would only be true if U dot V was 0. So we did show that AB and AC are perpendicular. But there's no reason why they can't be perpendicular and of different lengths. So you recognize this as a rectangle. And the rectangle has two diagonals that are the same length, but it's certainly not a square. So if you have a parallelogram with equal diagonals, then what you have is a rectangle. Now there's no excuse for this error in language, but I want to remind you that in carpenter or framing a window or a house, cabinet making, you frequently check that your frame is square by measuring the two diagonals. And when a carpenter says the frame is square, or a cabinet maker says they have a square frame, they don't mean they have a frame that is a square. They mean they have a frame that has four 90-degree angles. That the frame is square, not that the frame is a square. Now, I can't excuse their use of language by saying that, but I want to make sure you understand that you frequently point to an object like this and say the frame is square. Okay, thank you.